You know, when you hear data engineering, your mind probably jumps to optimizing ads, right? Or making e-commerce run smoother. But what if we took those exact same skills and pointed them at something way more complicated? That's what we're digging into today, the wild technical challenge of building data systems for criminal justice reform.
Yeah, so we're not talking about building a better Netflix queue here. The mission is, well, one source called it the forensic reconstruction of the criminal justice system. I mean, just let that sink in. The stakes are just unbelievably high. We're talking about people's actual lives and the transparency of the government itself.
So just how different is this kind of work? Well, think about it like this. Over on one side, you've got the commercial world, right? Everything's pretty clean, you're pulling data from nice APIs, and the goal is simple: make more money. But then you look at the civic world. Here, the goal is something huge, like transparency in a democracy. And your data? Oh man, you're lucky if you can scrape it out of some ancient, walled-off government system.
Okay, so before we can even get to the solutions, you really have to understand the sheer scale of the problem. So let's start at the very beginning, with the data itself. And let me tell you, it's a chaotic, fragmented mess.
So here's the fundamental problem for any engineer looking at this. All this crucial public information, on arrests, court cases, who's in prison, it all exists, but it's trapped inside what's essentially a black box. These are systems that were built for one thing: managing cases day to day. They were never, ever designed for analysis. So the mission? It's to crack that box wide open and transform all that chaos into something you can actually query and understand.
And this really shows you what that mess looks like in practice. Just think about one single person's journey through the system. Their data could be scattered all over the place. Some of it's in the state court network, but it's full of typos and inconsistencies. Then there's the Department of Corrections, where their ID doesn't even match. You've got dozens of different county jail systems that don't talk to each other. And then, get this, some of the most important info from the Pardon and Parole Board is literally locked away in PDF files. It's a nightmare.
So, confronted with all that chaos, how in the world do you build a single, reliable source of truth? Well, you can't just wing it. You need a blueprint, a really structured, principled way to build your data pipelines.
And that blueprint, that guiding philosophy, is something called a reproducible analytical pipeline, or RAP for short. The whole idea is to get rid of all that manual, error-prone stuff, like copying and pasting data in a giant spreadsheet, and replace it with automated code that's version-controlled. And this is so, so important. In this line of work, reproducibility isn't just some nice-to-have technical detail. It is an absolute ethical must. Every single finding has to be something that another person can check and verify for themselves.
Okay, so the map we're going to use for this whole reproducible journey is a concept called a directed acyclic graph, or just a DAG. Now don't get hung up on the fancy name. All you need to know is it's basically a series of steps where each step has to finish before the next one can start. It's both the map and the memory for the entire data pipeline.
Let's make that real for a second. A DAG just breaks down a super complex process into these really clear, dependent steps. So, step 1 might be scraping the raw data from a court website. Step 2, cleaning that data, can't even start until step 1 is totally done. Then step 3 analyzes it, and finally, step 4 spits out a nice report. See? Each step is its own little job, and the graph makes absolutely sure they run in the right order every single time. No exceptions.
All right, so we've got our map, the DAG. Now, let's talk about the actual tools in the toolkit. What do engineers use to navigate this journey? Especially since a ton of this kind of analysis is done in the R programming language.
Think about it. You've got this intricate map, your DAG, and it might have dozens, maybe even hundreds of steps. How on earth do you manage that workflow without going crazy? I mean, what happens when you make one tiny change that forces you to rerun hours and hours of work?
Well, for a lot of folks in this space, the answer's a brilliant R package called Targets, and its secret weapon is something called caching. See, Targets is smart. It understands the whole DAG, and it saves the result of every single step. So let's say you change something way at the end of the pipeline, like you just want to change the title on a chart. Well, Targets doesn't rerun the whole thing from scratch. Nope. It intelligently figures out what changed and only reruns the tiny bits that were affected. It's a massive, massive time saver.
But wait, there's another classic problem. We've all been there, right? A pipeline works perfectly on your laptop, but then you try to run it on a server and it just breaks. Why? Because of some tiny little difference in a software version. So the big question is, how do you guarantee that this data journey is exactly the same no matter where it's being run?
And that is where Docker saves the day. The easiest way to think about a Docker container is like a perfectly sealed, portable little box for our pipeline. It packages up everything you need: the code, the exact version of R you used, and every single system library. It's all in the box. And that's what guarantees your analysis is perfectly reproducible, whether you run it today or your colleague runs it 5 years from now.
So when you put all this together, you get a really sophisticated setup. The most bulletproof systems use what's called a hybrid pattern. You can see it here. The researchers and analysts are working in their inner loop, using targets to manage all their dependencies and just move fast. But then, for the outer loop, the serious production stuff, that's when tools like Airflow or Dagster take over. They handle things like scheduling the pipeline to run every day, automatically retrying if it fails, and screaming for help by sending alerts if something really breaks.
Okay, so you've built this amazing, robust system. But what happens when the real world just throws a giant wrench in the works? I mean, an event that completely redraws the map you so carefully built. This is where the pipeline really gets put to the test. And that's exactly what happened with the Supreme Court ruling that fundamentally changed, well, everything about the justice system in Oklahoma.
Back in 2020, the Supreme Court handed down the McGirt v. Oklahoma decision, and what it did was affirm that huge swaths of eastern Oklahoma are in fact still Native American reservation land. This wasn't a small thing, it was a seismic shift. All of a sudden it meant that for many crimes involving Native citizens on this land, the state of Oklahoma simply didn't have jurisdiction.
And for data engineers, this created a monster of a problem. Suddenly, knowing a crime happened in, say, Tulsa, wasn't nearly enough information. The new critical question became, which court system even has the authority to hear this case? Is it the state, tribal, or federal? And the answer to that question depends on a really complex mix of who you are and, crucially, where you were.
So how do you solve that? With a geospatial pipeline. Here's how it works. First, you take the address where an incident happened and you turn it into a super precise latitude and longitude coordinate, a dot on a map. Next, you take that dot and you overlay it on top of the official maps of the tribal reservation boundaries. Then a cool operation called a spatial join basically asks a simple question: is the dot inside one of the reservation polygons? And just like that, the pipeline can automatically tag every single case with the correct jurisdiction. So, let's take a breath. After wading through all that messy data, building these incredibly robust pipelines and solving some really tough geospatial puzzles, what's the payoff? What's the actual real-world impact? Let's see how all this hard work gets translated from raw data into decisions that matter.
Here's a perfect example. In a project looking at eviction filings, the engineers ran into a classic data problem. The same landlord, say Cobblestone Apartments, would be spelled a dozen different ways in the records. By building a pipeline to clean and standardize those names, they were able to reduce the number of unique landlord names by 12%. Now that might not sound like a lot, but it was absolutely essential for figuring out which handful of entities were actually behind a huge number of evictions.
And really, this is what it's all about. This is the ultimate goal. Having a rock-solid data pipeline means that researchers can finally use really advanced statistical methods, like this one called difference in differences. It's an incredibly powerful way to figure out if a new policy is actually working, or not. We're moving beyond just showing pretty charts with trends. This is about rigorously measuring the true impact of a policy, separating its real effect from all the other random statistical noise out there. It's how you turn messy data into actual proof.
Look, building these systems is not easy. It's a complex, painstaking process. There's no doubt about that. But when you combine that principled, careful engineering with a really clear mission, you can create a whole new lens to understand our most critical institutions. And that kind of leaves us with one big question to chew on. If this kind of forensic data work can crack open the black box of the justice system, what other black boxes out there should we be trying to open next?